Some of you guys may not have heard of town numbers, so let's start with an example here of a town number. I'm just going to choose n equals 56. Now, a town number is defined to be any number such that the number of divisors, the count of the divisors, is a factor of the number itself. Okay? Now, 56 is equal to 7 times 8, but that's 2 cubed times 7. And I'm going to put the 1 here for emphasis because it gives us a little bit of insight on how you count the divisors. You can list all the divisors, but a nice number theoretic way to do it is just write down d at n is equal to 3 plus 1, which is the first exponent you see there. And this is a fairly elementary counting argument, why this works, and then 1 plus 1. Right. So you see what we did is we just incremented both of the exponents that were present in the prime factorization of 56. If you carry out this multiplication, you get 8 divisors. And you could well list those divisors, but you add the 1 because you have to allow for a 0 exponent. Like, for example, if 7 to the 0 times 2 cubed is 8, which is a divisor, right? So that's why you have to allow. And similarly, for if you let 2 to the 0 times 1 is 7, 2 to the 0 times 7 is 7, which is also a divisor. That's why you have to increment right here, okay? Now notice that we do get the result, d of n divides n, right? 8 is clearly a divisor of 56. So 56 does qualify as a town number. Now what we're trying to show is that if p is the smallest prime divisor of any town number, and q is a prime factor, not necessarily another prime factor, but we think of it that way. Let q be another prime factor, but it works for p also. We need to show that q raised to p minus 1 divides n also as a factor of n, which is interesting to me. It took me a while to see why this works. But anyway, we're going to suppose the opposite of what we're trying. This is just kind of a classical contradiction proof. We're going to suppose, you see, we're trying to show this statement right here, that q to the p minus 1 must be a divisor of n. Since n is a town number, we're going to suppose the opposite. You see this negated relation here. It does not divide. Okay, it does not divide. Now, some big results here. The result follows fairly quickly, but that means that since q is known to be a factor of n, q raised to a power, q and q raised to various powers must be divisors of n, or this is a possibility at least, right? But it has to be for p minus 2, right? Because we've assumed that q, we assume that q to the p minus 1 does not divide n, okay? So that means the possible exponents here would be numbers between 1 and p minus 2 since we made this assumption. Now notice you may think, well, what about large ones? Well, really, if q raised to the p minus 1 does not divide n, that would imply that q to the p does not divide n, and so on. That, I probably should say p plus I, maybe, if you want to. Yeah, we could, yeah. Or p plus k. See, because of the transitivity divisibility, if this doesn't divide it, none of these can, I'll put a k here if you want, but you can't go for any higher exponents, right? Because that would allow q to the p minus 1 to be a divisor of n also by transitivity of division, okay? So these are your possibilities right here. I is equal to 1. I is trapped between 1 and p minus 2, all right? Now, so q to the I, we're assuming that I takes on one of these values, okay? But that implies I plus 1 is a divisor of d n, which is the kind, and it comes from this incrementing idea I just showed you right up here. You see, in other words, this part right here holds because of the fact that you have to increment the exponents. Okay. Now, so if you add 1 to both sides right here, you get 2 is less than or equal to I plus 1 less than or equal to p minus 1, right? And that's just straightforward inequality manipulation. Okay, I added 1 to all 3 of these objects here. Okay, now, so you see right here, it means I plus 1 must have a prime divisor less than p also. We'll call it a prime divisor r, right? I plus 1 is clearly less than p minus 1, right? Less than or equal to p minus 1. But it must have a prime divisor less than p if that's the case, okay? And you can see really quickly we're going to get this contradiction here because we know that r divides d sub n. I mean the count of divisors, but it's given that d of n is a divisor of n, right? So this would imply right here, just to be clear, r divides n, right? But you see, that r is a number that's less than p. We've already seen that also. R is a number less than p. That's just what we called it, okay? Since I plus 1 has to have a prime divisor, since it's greater than or equal to 2, right? So it's very cool. So this is a contradiction. This is a contradiction, which means that I lost my marker here. This is a contradiction. And what does it contradict? Okay, this contradicts the fact that we assumed that q to the p minus 1 does not divide n, right? So that means it does, and it's for any prime q, right? We play by the rules here. We get a contradiction based on this supposition that q to the p minus 1 does not divide our tau number, right? So since we reach a contradiction, we conclude that q to the p minus 1 does divide n, which is what we're trying to prove. It's a lot of words, but it really makes sense. You assume the opposite of what you're trying to prove. You reach a contradiction, which means what you're trying to prove is true. Okay? So that does it, folks. That completes the proof. I guess I should write QED right here. And I have a bigger, these are also called refactorable numbers. Let's see. This is an other tau number if you want to play with it. This is another tau number, and you can verify that it meets some conditions. I won't go through the work here, but this is a tau number you need to produce. I think it's 7 is a prime divisor, and of course 5 is. Maybe 3, 5, and 7. I think 3, 5, and 7 are the prime divisors of this. But you'll see it's a tau number because you will be able to calculate tau of the number and show from the prime factorization that it divides the tau number. Okay? So fun, y'all, this came from a book by a guy named Zelinsky. I think his name was Josh, but I'll just say Jay Zelinsky. I may be getting the name wrong. I don't know if there's any. I think it's just Josh Zelinsky. All right, very, very interesting. A lot of interesting things in that paper. Nice proofs. He defines everything very, very carefully and builds it up very, very nicely. And he proves something pretty interesting about the distribution. You know, he proves there's an infinite number of these tau numbers. He gets into their distribution. It's less than 1/2 of all the primes, less than a particular integer, I think, something like that. But it's a very good read, very well written, very thoughtful. The guy obviously reread it, circumspectly checked for typos. It was a very good paper. So read that if you're into this kind of stuff, because not until about a year ago, I didn't even know what a tau number was. I knew what the tau function was. But anyway, that is all.